Hey everyone, welcome back to MLWorks. In this video, we'll be discussing about contrastive learning, which is a self-supervised learning approach. And specifically, we'll be discussing the SimCLR framework and we'll also talk about the implementation aspect of it. So what is SimCLR framework is all about? So we'll understand this image because it captures all the relevant information the framework is talking about. So consider you have an image, which in this case is a cat image, and what you do is you apply data augmentation on top of it. Once you apply data augmentation, we move away from the original image and we generate something called as xi and xj, which are our transformed images. Now that is passed to an encoder and it will try to capture the representation of that specific image, and we get something called as hi and hj. Once that is captured, what we do is we try to pass that to an MLP network. MLP means multi-layer perceptron, which is also known as projection head in this case. And we generate our final embedding, which is Zi and Zj. Now what you do is at the end, once you get those embeddings, you try to compare them and see whether they are similar in nature. If they are similar, then the distance between them is less. So they are grouped together or they belong together as a class. So in this scenario, we are not having any information about the labels of the data of the images. What we do is we generally just take the images and send it to the model, and it will understand the representation between those images, whether they are similar in nature or not. If they are similar, then they are grouped together, and if not, they are kept far apart. Now that's the basic idea of SimCLR framework. Now let us understand how to implement this SimCLR framework with Lightly. Lightly is a Python package for self-supervised learning. So we'll try to use that and understand how to implement SimCLR. So the first part of the implementation is importing the packages. So the key packages involves Torch, PyTorch Lightning, torchvision, and then Lightly. Lightly contains your key, the dataset, and also it contains the SimCLR transformation that you have to apply on your dataset and then train your model. So once you have installed all these packages, you can import them. And I have all this up and running, so I have imported them. Now, since this is a model that I'm training, it may take time. So what I have done is I have already trained the model. We'll just look at the code and understand what is happening. So once we have imported the packages, next we set the experiment config, which in this case is first is num workers, which is set as 4. This is used for loading the data set, and then we have batch size of 256 and the seed is equal to 1 for reproducing the experiment, and then max epochs that we are setting is 20, and the input size that we want to resize our images is 128 cross 128, and the number of filters is 32 filters I mean. So let me run this as well, and let me run this again. So I have already downloaded the dataset from this repo, and what I do is then just give the path of that specific dataset here. Now let us understand the key concept of contrastive learning. So SimCLR is based on contrastive learning, and which learns by contrasting the positive and negative samples. So when they say positive and negative samples, it means a cat image compared against cat image is called a positive sample or positive example, and when a cat image is compared against a dog image, it is considered as a negative example. So in SimCLR, two different augmented views of the same images are considered as a positive pair, and while the different images are considered as negative pairs. So different images means dog and cat, same image means cat and cat. So SimCLR relies on a strong data augmentation. So since we are using different, since the whole idea of SimCLR is based on the augmentation, strong data augmentation techniques are required to generate different views of the same image. So what we do is we do random cropping, color jittering, and Gaussian blur, and create different augmented views of the specific image. Okay, now when it comes to the encoder network, what we do is we use ResNet 18 and get the final latent space for each of those images. and the projection head is nothing but your MLP, which is multi-layer perceptron, and get the final embedding from this. And we use something called as a contrastive loss, which will, what it will do is, when there are positive samples, it will try to keep them together, and it penalizes those images which are dissimilar in nature. Okay, so this is the key concept of the whole paper and the key idea that we have to understand. Now once we understand this, what we do is we apply transformation, SimCLR transformation first. This is for training data set, and then we use this transformation for the testing data set. Okay. So here in the training dataset we pass VF and RR, which is nothing but vertical flip. 0.5 represents the probability and RR represents the random rotation, again the probability of 0.5. And by default there are other augmentation which is applied in SimCLR transform that we are not looking at it because there are a number of ways of transformation can be applied. So we are not looking at all of them, we are just looking at the two. So once this is done for SimCLR, what we do is we apply transformation through torchvision transforms, and here also what we do is we resize the images to 128 cross 128 and turn it into a tensor, and then normalize the values of our images by mean and standard deviation. Next, what we do is we apply this on the data set, the transform that we have created here. We are applying it on the data set transform, and this is on the test transform on the test data set. Okay, so once this is done, what we do is we create a data loader, and what it will do is it will keep it ready for your training, this one. So what we do is we pass our data set and the batch size. We want to transform our number of batches it has to create, and then we want to shuffle, drop last. If there are some images which are beyond the batch size, then it has to drop those. Num workers has 4. Okay, so this is data loading part. Now comes the part where we create our model. So what we do here is we create something called a SimCLR model, and it inherits the properties of PyTorch Lightning. So what this will make is that all the logging of parameters, even the way the epochs is running, all those things will be abstracted away from us, and it will be taken care by PyTorch Lightning. So in the init method, what we do is we take our encoder, which is the ResNet 18, and we finally get the feature vector from this one, final, which is the backbone. So once we get the backbone, what we do is we get the size of the embeddings that is getting, right, the input features that we get. What is the size? That is, it will be basically 512. So what we do is finally we transform that 512 to 128. Okay, and then we have a criterion for the measuring the loss. So for that we use this normalized temperature scaled cross entropy loss, which is again nothing but it will try to keep the positive examples together and while the negative samples too far apart. Okay, so this is your initialization of SimCLR, and here we have the forward pass where we take in the input, pass it to the backbone, which is nothing but your ResNet, and then we flatten it and make it one-dimensional. And then we pass that one-dimensional to projection head, and this will create our final embedding. Okay, so this is your forward pass. And during the training step, what happens is we take two pairs of, every time, right, we take a pair of images and send it to the model. That is the forward pass. And we create our x0, z0 and z1 and calculate the distance between them, and then see what is the loss. So here this is the training step, and next is our optimizer, which is stochastic gradient descent, and where we are applying learning rate followed by momentum with weight decay. And this is how you the weights updates are happening, how it has to update the weights. And then we are also using something called as cosine annealing learning rate. What it does is initially the learning rate will be high, okay, and as the epochs increases, the learning rate slowly changes or drops, such that it is not first, since it is high because we want to avoid staying in local minima. Okay, so that's why initially it is high, the learning rate is high, and it slowly decreases as the number of epochs increases. So at max, what we have is max epochs is 20. So it will try to change after every epoch. It will update the learning rate and make it slower or smaller, the learning rate. Okay. So now what I'll do is, I won't train the model because it is already trained and it takes quite some time, like around 4 minutes 37 seconds. So I won't do that. So what we do here is we initialize our model and then we pass it to trainer. Okay, so pl.trainer, we create an object called trainer, and where you have this fit method and pass the model, and we have our training data set. So for the trainer, what we do is, what is the number of epochs and what device we want to use, either it is a GPU or CPU. Okay, that we mention it here. And once we have created an object for trainer, then we fit the model and the top of the data set. And it will show, okay, while you are training it, it will show what you are using. Either it is using a GPU, TPU, HPU, or number of devices that you have, and what is the number of parameters on each of those modules that we have created. The backbone, which is the ResNet, it uses 11.2 million parameters. Projection head, it has around 328k parameters, and criterion has 0 parameters. And what are the trainable parameters and what are total params? Okay, so this is where you train the model, and once you have trained the model, what we do is we want to understand. Now, given an input image, and after you transform it by using data augmentation, you want to understand whether those two images are equal or similar in nature or not. So what we do is we create multiple helper functions. So here what we do is, first we generate embeddings. What this will do is, given an input image, okay, it will generate the embeddings for it. And it is quite simple to understand, because here you have two lists you are creating. One is containing the embeddings and the other is containing the file name. And you are loading the model with, in this context manager, torch.nograd, such that you are not performing back propagation. Okay, then you are iterating through the data and you are passing that to the images, passing all the images to the model, and then you are generating the embeddings, and you are also fetching the file name simultaneously. And then you concatenate the embeddings and normalize the embeddings and then send that as the output. Okay, so I'm also not running this. Okay, let me run this as well, because I think we are doing a couple of things in the next steps. So I think we might have to run this again. So here we have this model. Okay, this takes around 36 seconds. So let us wait for 36 seconds. Okay, so it is done. Now what we do is, we have created the embeddings. We have the corresponding file names inside those specific lists which we mentioned earlier. Okay. Now what we do is we create another helper function where we transform the images into a different format like NumPy array, and then we try to plot it using this function plot KNN examples. So what we do here is we apply something called as k nearest neighbor and on top of the embeddings, and it will try to select the 3 nearest examples given a set of embeddings. Okay. Here we are doing it for the 6 samples, and the nearest neighbors that we are looking for is 3 neighbors. So let me run this, and let me run this. Now here, if you notice, it is based on the color. It is able to fetch all these images together. Okay, so they all look almost similar in nature in terms of color at least. So it has tried to group them. Okay, it's like shoes or sandals, and okay, and you have this based on this color, they all look similar in nature. So yeah, this is the corresponding score for each of those images as well. Okay, and So we are at the end of the video. Okay, so I hope you have understood what a SimCLR framework is and how it tries to understand the unlabeled data set and tries to group them. And with that, I'll conclude this video. Thank you for watching.